Across the vast expanse of the cosmos, amidst swirling galaxies and shimmering nebulae, lie the birthplaces of stars, giant molecular clouds. These immense clouds, composed primarily of hydrogen and helium, are the fundamental building blocks of stars. Imagine, if you will, a cloud billions of miles across, a cosmic nursery teeming with the raw materials for creation. Giant molecular clouds are not merely massive, they are also incredibly cold and dense, far colder and denser than the air we breathe. It is within these frigid depths, shrouded from the glare of distant starlight, that the seeds of stars are sown. These clouds, often invisible to the naked eye, can be detected by radio telescopes, which reveal their presence through the faint whispers of molecular emissions. These clouds are not static entities, but dynamic and ever-changing, sculpted by a complex interplay of gravity, turbulence, and magnetic fields. Within these cosmic cradles, stars take their first tentative steps towards existence. Over eons, these clouds undergo a series of transformations, collapsing and fragmenting to give rise to brilliant stars that illuminate the universe. A giant molecular cloud, despite its immense size and density, exists in a delicate equilibrium. The inward pull of gravity is counterbalanced by the outward pressure of gas and magnetic fields. However, this equilibrium is not meant to last. Like a stone dropped into a still pond, disturbances ripple through these clouds, upsetting the balance and setting in motion a chain of events that culminates in the birth of stars. These disturbances can arise from a variety of sources: the shockwaves from a nearby supernova explosion, the gravitational tug of a passing galaxy, or even the collision of two molecular clouds. Imagine the energy unleashed by such cosmic events, the sheer power that sends shockwaves reverberating through these stellar nurseries. As a shockwave propagates through a giant molecular cloud, it compresses the gas and dust, causing the cloud to fragment into smaller, denser clumps. These clumps, now subject to their own gravitational pull, begin to collapse inward, pulling in more and more material from their surroundings. This fragmentation is crucial as it determines the number and mass of stars that will eventually form. As the fragments of a collapsing cloud continue to contract, their densities and temperatures increase dramatically. The once frigid gas and dust heat up, radiating energy into space. This embryonic stage marks the birth of a protostar, a celestial object on the cusp of stardom. Imagine a protostar shrouded in a veil of gas and dust, its core glowing ever brighter as it gathers mass and heats up. The journey from protostar to star is a delicate balancing act, a battle between gravity's relentless pull and the outward push of radiation pressure. As a protostar accretes more material, its core becomes denser and hotter, generating intense radiation pressure that tries to push the infalling material back out. This struggle for dominance, this cosmic tug-of-war, shapes the destiny of the nascent star. Over thousands of years, the protostar continues to contract, its core temperature and pressure steadily increasing. The fate of a protostar, whether it ignites into a brilliant star or fades away into obscurity, depends on its mass. Only protostars that accumulate enough mass can generate the core temperatures and pressures necessary to ignite nuclear fusion, the engine that powers stars. Deep within the heart of a protostar, a remarkable transformation is about to occur. As the core temperature and pressure reach a critical threshold, a process known as nuclear fusion ignites. Imagine the moment of ignition. Hydrogen atoms, the simplest and most abundant element in the universe, are forced together under unimaginable pressure, fusing to form helium and releasing a tremendous amount of energy. This energy, released in the form of light and heat, pushes outwards, counteracting the inward pull of gravity. A delicate equilibrium is established, a balance between the crushing force of gravity and the outward pressure of nuclear fusion. This balance, this cosmic dance, marks the birth of a star, a luminous beacon shining brightly in the vast expanse of space. The birth of a star is not the end of the story, but rather the beginning of a new chapter. Stars are the building blocks of galaxies, their light and heat shaping the cosmos around them. They forge heavy elements in their cores, elements that will eventually become the building blocks of planets, moons, and even life itself. And so, from the remnants of dead stars, new stars are born, continuing the cycle of stellar evolution and enriching the universe with the elements necessary for life to flourish.